One of the things I'm doing with my X4R receiver is I want to set up voltage monitoring. I've talked about the fact that I have voltage monitoring on the OSD, but sometimes if I'm busy flying, I might not notice. It happened at least once. I accidentally plugged in a battery I had already discharged and started flying and didn't notice that my voltage was getting low. I was just looking at my discharge and oh, that doesn't sound right at all, does it? I was looking at my milliamp hours, and since they hadn't hit the target yet, I didn't notice the fact that my voltage was down around 9 volts on a 3S battery. So, so I always like to have backup voltage monitoring on my Tyrannus because my Tyrannus can say A1 critical, A1 critical, and I'm like, oh, hey, that's not right. Now, I ran into a problem where if you have a NAS board, you cannot run SmartPort telemetry off of soft serial because it runs at 57 kilobaud, 57.6 kilobaud, and SmartPort soft serial can only go up to 19.2 kilobaud. So that's it's just showstopper there. You have to use a hardware UART to do SmartPort telemetry. And since I only have two hardware UARTs and I'm using them both for SBus and Blackbox, I'm out of luck. At least on a NAS. On an F3 board, you have more hardware UARTs and more options, and could do that. So fine, no telemetry. But really, the only thing I wanted the telemetry for was the voltage monitoring anyway, and RSSI monitoring. But of course, that's built into the receiver. You don't need to integrate that with the rest of your system in any way. And since the X4R has an analog input, that can be accomplished. Now, if you want to run voltage monitoring on your X4R, you can get a SmartPort voltage sensor, or you can just hook the analog sensor in to your system pack voltage. But in order to do that, the analog pin is only rated up to 3.3 volts. It's a 3.3 volt sensor. So if you plug that directly into heck, even a 1S battery, you could blow it. So what you need is a sensor like this. And this quote-unquote sensor is really nothing more than a voltage divider. It's got three pads here for, I think it must be 1S, 2S, 3S. I'm pretty sure it only goes up to 3S. The one I have anyway does. Anyway, and it's just a voltage divider just takes the incoming voltage and outputs a fraction of that voltage. So, for example, if we pull up the calculator, if we had a 3S system which goes up to 12.6 volts, we divide by 3.3 volts, and we would need to have a 3.8 divider. We would need to divide the incoming voltage by 3.8 to make sure that the incoming voltage never was higher than 3.3 volts. And in reality, you'd want to put a little bit of buffer on that. So you might say, instead of setting your cutoff at 12.6, you might say 13.5 volts or maybe 14 volts divided by 3.3 to get your division. So you would basically want a 4-to-1 division, and then the output voltage would never go higher than 3.3 volts, and you would not blow your sensor. But like I said, this sensor only goes up to 3S. It just doesn't have the right combination of resistors on here to divide a 4S voltage. So for example, I'll go back to the calculator. Let's say that 12.6 divided by 3, let's 0.3. Let's just forget about our safety margin here. We get 3.8. Well, if we take 3.8 and if we have a, let's see, 4.2 times 4. If we have a 4S battery divided by 3.8, we would have 4.4 volts going into that sensor, which of course is more than 3.3 volts, and it would blow it. So we need to build our own voltage divider. And fortunately, it's really easy. First, we're going to go to a voltage divider calculator, which is going to give us the value for the two resistors that we need to make the voltage divider. So we're going to say we want our output voltage to be 3.3 volts. And let's just put a little bit of safety margin in here. Let's say something like 3.1 volts. Right? We're just going to always leave a little safety margin. And then our input voltage, let's say, I think we said, sorry, I've run off 3S. I don't have the 4S voltages in my head. 4.2 times 4, 16.8, 16.8, and we compute. Well, so actually what matters is not the absolute value of these two resistors, but the ratio between them. So in fact, hitting compute here, there's no right answer. We have to give it at least one of these resistor values. So let's say that one of the resistors is going to be 1,000 ohms, and the other one is going to be 4,400 ohms. Now, in reality, resistors come in various standard values. So in reality, what we have to do is we have to pick the closest standard values that are going to give us the desired output voltage. Uh, and I'll show you what I actually ended up doing right now. So here's the voltage divider that I've built. And in order to let me operate this one-handed, I've got one lead just clipped up here. And you can see that one of these resistors is around 47K ohms, and the other resistor is around 4.7K ohms. So in other words, this resistor is 1/10 the value of this resistor. There's a little bit of variance in there. I believe these may be 5% resistors, which means they have 5% tolerance. So there's nominally 47K, but it's actually a little different. And because there is a 10-to-1 ratio between the ground side resistor and the hot side resistor, the output voltage is going to be reduced by a ratio of about 10 to 1, or 1/10. So in other words, 12.6 volts going in would come out as 1.26 volts, more or less, coming out. And that means that if our sensor pin is rated up to 3.3 volts, then in theory we could have up to 33 volts, which would mean that this sensor would be good for up to 6S voltage. Now in reality, you could get a little more resolution by using a lower divider. This is more division than we really need if we're only, say, going up to 4S. But since there are standardized resistor values, it would require a little bit more bodging around to get the exact ratio I want. A 10-to-1 ratio will probably still give you plenty of resolution for what you need to do to know if your batteries are too low, and will mean that you are just absolutely protected against any potential voltage spikes or anything like that. I will now take this off of here. Let me just show you what I've built here, and of course you can look up a circuit schematic on the internet, but it's really simple. You've just got the high value resistor here. So this is the 47K resistor, and it's going to the hot input, the battery voltage. And you've got the low value resistor here. This is the 4.7K resistor, and it's going to ground. And you just wire them together, and you run out to the sensor from the central point. And then I've also got the ground line hooked up. Strictly speaking, this is not required because the receiver will be getting ground from wherever it gets its power from. But I went ahead and did that just in the interest of thoroughness. So that's it. It's roughly a 10-to-1 voltage divider, which gives you, basically you can run up to 33 volts into that analog input on the X4R without blowing it. Oh, one other catch here. The X4R puts that analog input on A2. Some of the other FrSky receivers put the analog input on A1, which was a little bit confusing to me until I figured it out. But yeah, if you're adjusting A1 and it's not doing anything, it's because the X4R puts that analog input on A2.